Okay, welcome back to Real Analysis. If you recall, what we've been doing so far has been to develop a lot of the groundwork for constructing the real numbers. And in particular, last time, we actually showed what the construction was for the real numbers. And it was motivated by noticing that the rational numbers, we know the rational numbers are ordered, they have an arithmetic, but there are gaps. Okay? In particular, not every bounded set has a supremum. So, for instance, we think about the rational numbers as being ordered on a line. But we noted, for instance, that there are some lengths that do not appear as a rational number. So if we call this length of the hypotenuse of a right triangle 1, 1 triangle, if we give this a name, square root of 2, which we don't even know what this term means, but if I just call it this by this symbol, this length actually lives somewhere on this line, but it's not represented by a rational. In particular, it might be this particular length, which we're calling square root of 2, for reasons that will become clear later, lives on this line, but it's not, there is no rational at this particular length. Now, how do we actually get at the gap here without referring to the actual point at this gap? That's the question. And so if you take a look, for instance, at all the rationals, there's lots of rationals that actually get really close to the square root of 2, don't they? Okay? They sort of, in fact, encroach on this particular length. But there's nothing right here. So how do we get at the gaps? One of the problems with the rationals is that because the fact that it has gaps points out the fact that not every bounded set has a supremum. In particular, this set of rationals to the left of this particular point does not have a supremum. It does not have a least upper bound. That's what supremum means. So we noted that the rationals don't have what's called the least upper bound property. A set has a least upper bound property if every non-empty subset that's bounded above has a least upper bound. Okay? And of course, we're always referring to the particular set we're interested in. So when I say has an upper bound, I mean in the set S. When I say it has a least upper bound, I mean in the set S. And if S here in this statement is replaced by Q, it's not true, okay, as this particular set shows. Okay, good. So the idea then is to try to fill in these gaps somehow. And how would you do that? Well, if we fill in the gaps, we hope to get something that we would think of as the real numbers, but how do you do that without referring to the gaps themselves? Well, the idea is, if I want to get at this particular endpoint, I can do so by just looking at the rationals that in fact approach this endpoint, right? And just calling that, referring to the endpoint by the rationals that lead up to it. Okay? That's the idea of a cut, a Dedekind cut. A cut is, you just think of actually cutting the rationals at a particular point and looking at everything to the left. So a cut is a subset of rationals that's not trivial, so it's not empty and it's not everything, not all the rationals. It's closed to the left or closed downward, as we might say, and it has no largest member. Okay, that's what a cut is. And then the real numbers will just be the set of all cuts. Okay, this is what we saw last time. Okay, so there are some things that remain to check. From last time, what we saw is the following. So what we did with these cuts is we defined an order. Do you remember how we defined an order of cuts? If you have a couple of cuts, that looks something like this, how did we define whether one was less than the other? If one is included in the other. Good. So defined order was basically by inclusion. Okay, it was a very nice notion of order. We also defined an arithmetic, which includes the operations plus and times. Okay? And these were notions that we developed that were what you might expect. In particular, if a cut is a collection of rationals, if I have a cut alpha and a cut beta, then their sum is basically going to be all sums of rationals, one from alpha, one from beta. With me? Okay. That's what we defined addition to be. And multiplication was defined somewhat similarly. You just had to worry a little bit about the signs of multiplying things that are negative. So you define them first for positive reals, and then you defined them for negative in the natural way. Okay, so this is something we won't do, but I encourage you to just think about how you would do this and try it if you like. Check that this is in fact an ordered field. Okay, so we've defined R. So check that R is, we know it has an order, and we see it as a field, but does the order play nice with the operations of the field? And the answer is yes. Okay, we can think about this actually, just without writing it down. You give me a cut, let's call it alpha, and suppose it's less than beta. So that means the set of rationals is actually included in this set of rationals. So here's alpha, here's beta. Okay, now, is it the case that if I add something to alpha and the same thing to beta, that order is preserved? So this is alpha, this is beta. If I add another cut to this cut, what's the effect on this cut going to be? Shifted, either left or right, right? Well, if I add the same cut to this collection, what will it do? Shift it also. Is order preserved? Yes. So we see order is preserved by addition. Multiplication, I encourage you to think about why that's the case. Okay, so it is in fact an ordered field. So what we'd like to do next then is verify a few other properties about R that I claimed were true last time. Okay, so in particular, does R contain Q as a subfield? And the answer is yes. It extends the rational numbers, the real numbers do. So let's see why that's true. To show that R actually extends Q as a subfield, what I mean is there a natural way that the rationals sit embedded in this construction where we think about R as a collection of cuts? So which cuts correspond to the rational ones? Well, if the idea is to associate to points on the line the rationals to the left of it, then which collection is going to correspond to rational points on this line? Paul?
Every cut that has a least upper bound in the rational.
Okay, or if you like, I don't want to refer to least upper bound yet. I could just think of all the rationals less than that particular rational. Okay, so let's then associate to some rational little q in big Q. What cut? Well, I'm going to associate to this the following cut. It will be the cut which I'll call Q star just to remind ourselves this is actually a collection of things, which will be rationals in Q such that the rational is less than the number Q, the rational that I want to represent. Okay? This is clearly a cut. And the claim is this association shows how Q is embedded in the reals. Okay? So here's one thing that, again, I'll ask you to check. It's not hard to do this. That the function that takes rational numbers into the real numbers, which we're thinking of as a cut, as cuts, that takes little q to little q star. This particular map is, if you took algebra, you would think of it as an injection of one field into another field. If you haven't taken algebra, what we're just going to verify is, in fact, these things preserve the field operations and do so in a one-to-one way. So check that this function preserves plus, times, and order. You can check that pretty easily. What do I mean by that? E.g., you give me a rational. If I add two rationals and I look at their associated cut, I claim it's the same as if you look at the cut associated to one plus the cut associated to the other. Okay? Or, for instance, if one rational is less than another, then their associated cuts will be less, one will be less than the other. One will be included in the other. Okay? You think about this just for a second, you'll see, yes, this is in fact true. Okay? These kinds of properties are true. Okay. It's also an injection. That is, it's one-to-one. You'll never have two different rationals getting associated to the same cut. Can you see why? Let's take the rational to 1 and the rational 4/5. Could they be associated to the same cut? No, because the set of things to the left of them is different. One will have more things than the other. Okay? Okay, so and as an injection is one-to-one. Okay? Okay, good. So, in fact, R does contain Q as a subfield. So you can think of then as then Q, I'll call it Q prime, which is basically the set of all Q stars such that Q is in little q is in Q, is a subfield of R. Okay, what I want you to do is step back from this and just appreciate for a second what we've just done. We've defined an object that looks like the real numbers we know and love, which is that was our goal, right? It sits along a line, it has an order, it has an arithmetic, and some of the things in it behave like the rationals. Okay, and it's defined completely in terms of rationals. A cut is a collection of rationals. Okay? Now, once we start working and elucidating the properties of the real numbers, we'll stop thinking of them as collections of rationals. Okay? Just like when we work with fractions, we don't think of them as ordered pairs, right? We think of them as fractions, okay? Because we have properties associated with them. But what have we done? We've constructed real numbers. The rationals sit inside in a nice way. Now, some of you may be objecting, or at least wondering, wait a minute, what about this funny thing we call the square root of 2? So notice, this length, which we've called by this funny symbol, it actually sits in this line as what? Well, it's a certain cut. Which cut? Well, it's the cut that consists of all rationals such that what? The square is less than 2 Or, just to make sure it's a cut and closed completely to the left, I should probably add what? All the rationals less than 0. Okay? So, for instance, if I give this cut a name, let's call this cut gamma. You can check using the definition of multiplication that, in fact, gamma squared actually will equal 2. Really? What was the definition of multiplication? Well, it looked something like, look at all products, possible products, at least for things that are considered to be positive, all possible products of pairs of things, one from one cut and one from the other, which is in this case the same thing. And is it not the case if you take a bunch of those, you'll get something that basically creeps up on 2 instead of creeping up on this length? So this creature lives in R, this particular length. Okay? Kind of beautiful, right? We have the possibility of solving equations like this one. Okay? And maybe even to drive home this point, we can say this a different way. See, gamma squared equals 2. Actually, this is 2 star, right? It's the cut that is associated to the rational 2. Okay? Oh, nifty. Very nifty. Okay. What have we done? We've shown that R extends Q. We've shown that R is an ordered field. And then the last thing that we wanted to show from the theorem, the big theorem we pointed to last time, theorem 1.19 in your book, is that R has a property that Q doesn't. R has the least upper bound property. And what we saw from last time is we could actually define or we could actually see what the least upper bound property, least upper bound is for any collection that has an upper bound, and we'll do so in the following way. Let's say A is a collection of cuts. Those are real numbers, okay? And we wish to take their supremum, and to show that something has the least upper bound property, we want to show that if the set is bounded, then it has a least upper bound. Okay? So I'm going to assume that this collection of cuts has an upper bound. So the upper bound here, maybe I'll call it beta for bound, with upper bound beta. So here's the picture you should have in your head. I've got a whole collection of cuts. And I'm just drawing a bunch of these here. And you're supposed to think of all the rationals that lie inside these things. If I have a whole collection of cuts, and these are all bounded cuts, they're bounded, let's say, by some beta. Okay? Then what is the supremum, or what is the candidate for the supremum here? I claim the supremum exists, so we should come up with a candidate. We said this last time, what the candidate should be. Let's look at the set gamma, which consists of what? What should the upper bound, what cut would correspond to the least upper bound of all these yellow sets? The green set beta is an upper bound, but there's a least one. Okay, there's one that includes all the other ones. Beta does. What's the smallest set that does? Beta may not be the smallest. Yes? Good. Take the union of all the cuts. So let's union as a set, the set of all alpha, where alpha is in A. It's the union. And notice that this is a subset of Q. Oh, really? Hey, that's kind of nifty. I guess that kind of makes sense. If we look at our picture, that particular union would look something like this, wouldn't it? It might be, of course, you could imagine a bunch of these sets sort of increasing with more and more stuff in it. But if there is a least upper bound, it might look something like this one that includes them all. Okay. Now, I have a subset of rationals. And I was thinking of this as a candidate for the supremum, but the first thing I better check is that gamma is what? Well, first of all, I want to check that it's a real number, that it's a cut, right? So you should check that gamma is a cut, and then check that gamma is, in fact, the supremum of the set A. Okay. Okay, now I realize this is beginning to feel a little abstract, but after this lecture, we won't have to think about collections of rationals when we think of real number. We'll think of properties. I know if I have a bunch of real numbers, I could take the supremum, right? Okay, but we're seeing where this comes from in this construction. Gamma here is a cut. It's a union of a bunch of cuts, and I claim it'll give something that is not just a cut, but the least upper bound of the set of cuts. So, why is gamma a cut? There are three things to check. First thing to check is gamma is non-trivial. Secondly is closed downward. Third is no largest member. I claim these are all things that you can see. We won't write them down because they are written carefully in your book. But let's just see if they're believable. First of all, why is gamma non-trivial? Can you see why gamma isn't empty? It contains a bunch of alphas, each of which is not empty. Excellent. Why is gamma not everything? Because there's an upper bound. Notice if there wasn't an upper bound, gamma might have been everything. Okay? So I'm just going to point out that it's non-trivial because it's a union of cuts. It's a union of cuts. And it's bounded above. And it's bounded. These are both the ingredients that are needed, okay, for non-triviality. Why is it closed downward? That should be readily apparent as well. It's a union of things that are closed downward. So if you pick one thing in gamma, because it's in a union, it means that that thing must be in some alpha, right? So then everything to the left of that thing must be in alpha. Therefore, everything to the left of that thing must be in gamma. Okay? Why is there no largest member? Again, if you pick something in gamma, it must be in some alpha. But alpha has no largest member, therefore it has something bigger than it. Therefore, that thing's in gamma. Okay? With me? Good. So it's closed down, and it is no largest element. No largest. This follows from since each, let's say each little x in gamma is in some alpha. That's probably enough to jog our memories about why this is true. Okay, great. So it's a cut. Now, let's see why it is a supremum? Why is it the least upper bound? First of all, is it clear that gamma is an upper bound? If it's a union of things. And if order is inclusion. Is it clear that gamma is an upper bound? Yeah, it contains everything. Okay, so here we go. Gamma is a cut. Gamma is an upper bound, clearly. Okay, so yeah, one has to be very careful with the word clearly, because it may not be clear to the reader, right? But should be very, very clear in the sense that, let's remind the reader, since gamma contains all the alpha in A. And we said order was given by inclusion. Okay? Happy? What's the last thing we need to check? Gamma is the least upper bound. It's the smallest in some sense. There isn't anything smaller. So let me draw a picture here to help us. Here is gamma. Okay? And it came from the union of a bunch of yellow sets here. But I want to show it's the smallest. What are some strategies I might employ? The smallest upper bound. Well, I could show that if there were something smaller, it's not an upper bound. So help me from this picture. Sorry, let me throw in just a few of the alphas here just to suggest a picture here. These are a bunch of the alphas in A. Now, let me pick something smaller than gamma. Oh, how about this cut? I'll call it delta, which is less than gamma. Oh, this looks too similar. Delta, which is less than gamma. Give me an argument for why delta is not an upper bound from this picture. So let me put a few bullets here. Here's the next bullet. Gamma is a least upper bound because if delta is less than gamma, thank you, almost rewrote that, then what does it mean for delta be strictly less than gamma? It means that there is something in gamma that is not in delta. Let's give it a name. Oh, let's call that element X. It is in gamma. It's not in delta. But the fact that it's in gamma means that it's also in what? Some alpha. Okay. So why is delta not an upper bound for all the alpha? Because it's not an upper bound for that alpha. With me? So I'll write that down briefly here. If delta is in gamma, then there exists an X that's in gamma minus delta. This is the set minus. Oh, then X is in some alpha in A. But then, and it's not in delta. In delta, so X, a delta, is not an upper bound. An upper bound for A. Okay, happy with that? Okay, so let me remind us what we have now. We have an ordered field. It extends the rationals, and it has the least upper bound property. Okay? And in fact, I claim that this actually characterizes the real numbers. There is no other field that, in fact, is an ordered field and has the least upper bound property. So let me summarize this by restating the theorem, which is in your book 119. R is an ordered field. It extends Q, and it has the least upper bound property. huge result, and something that's not something we're not going to prove. It takes a little more work, but it's good to note is, in fact, there is no other field with this property. R is the only, in fact, the only ordered field with the least upper bound property. Okay, so if you see any other field with the least upper bound property, I claim it is in some sense isomorphic to R. You'll be able to find a way to map the elements of that field into the elements of R in a one-to-one and onto way that preserves all the field operations. All others are isomorphic, with these properties are isomorphic to this one. Okay, so there's some amazing things that follow from having the least upper bound property. So let me show you a very cool consequence. Now that I know this, I don't have to think about real numbers as subsets of rational numbers, right? I mean, this was a construction that showed us how to define the reals in terms of things we've defined before. But now, look, I could think of, if I want, this particular length, which we're calling the square root of 2, for reasons that have to do with this equation, I could think of this as a supremum of a bunch of rational numbers, right? A supremum of a bunch of numbers, right? You can't stop me from thinking about it this way. Supremum of the collection of numbers that begins, let's say, 1, 1.4, 1.41, 1.414, 1.4142, etc. Okay? Right? And I claim that's exactly what the decimal representation for a real number is doing. Right? The shorthand for this, for saying let's take the supremum of these creatures, the shorthand is to write this as 1.4142.135 ... What this means is, give me the real number that is the supremum of this collection of rationals. Okay? That's what the decimal representation is. How do I know this supremum exists? Because of the least upper bound property of the real numbers. Are you with me? So now you can think of real numbers as decimal representations, and you sort of know where this comes from. Okay? Okay. That's certainly one way to think about it. Of course, there's lots of other ways to define this particular length, but that's one. All right. Any questions so far about our construction of the real numbers? Let me point out a few, something maybe even a little more general. So maybe more generally, you know, we constructed square roots here, right? You could convince yourself that if I want something whose square is 5, I could find that something, couldn't I? By making a definition very similar to that, or a definition very similar to, to that, but I could use supremum. So, for instance, I could define the nth root of a to the 1 over n. I could just define this as the supremum of all rationals whose nth power is less than a. Roots exist. That's really what I'm saying. Okay? And why can I do this? Well, this is a real number. It's a supremum of a bunch of rationals, each of which is clearly bounded. Real numbers have the least upper bound property. I know that supremum exists. Okay? And of course, what you have to convince yourself of is that when you multiply this together n times, you will get a. Okay, so that takes a little bit. That takes a little bit of work. Okay, but it does what you can what you expect. So you can check that if you take this creature, raise it to the nth power, you will in fact get the thing that's equivalent, the cut that's equivalent to a. Okay. Question, yes.
Do you have to make some sort of rule that says, like, they'll try and take this for -1? Because that's not going to happen, obviously.
Oh, interesting. Yeah, so the question is, what if I tried to solve the equation gamma squared equals -1? What if I tried to solve that? Yeah, that is an excellent question. So in this particular definition, I should probably be a little careful here to point out that what would happen if, this was 2 and this was -1? What would go wrong with this definition? It's not a cut. Why not? What's not a cut? Well, yeah, actually what I'm thinking about here is the supremum of a bunch of real numbers, right? So I wasn't even thinking of this as cuts. I was thinking, rational numbers. Yeah, maybe. Here, let me do R and Q. Right? But part of the problem is that this set would be empty, wouldn't it? Right? All these there wouldn't be. You wouldn't be take the supremum of anything, right? This set would be empty if. So we need here, in this case, a to be bigger than 0, else the set is empty, and the supremum won't exist. Okay? So we don't have a way yet of dealing with finding solution to this equation when the right-hand side is negative. Okay? We will in very, very, very soon. Okay? Yes?
Well, the definition still holds for odd or odd
Yes. Okay. So the question was, what if n were odd? So, for instance, if this is the third root, then this would be what? R cubed is less than something negative, which let's see. So I want to be a little careful here because in that case, if this were negative, let's say -1, and I put in a number like r equals -100, -100 cubed is still less than -1, and it would be in this set, which would still be fine. Yeah, I think it works fine. Yeah, so need a bigger than 0. So let me preface this. So you're checking all the boundary cases here, which is good. If n is even, how's that? Then that would be a true statement. All right, thanks. Lots of great comments. Okay, good. So let's talk about the counterpart to the supremum. We have a name for this. So we have a least upper bound. There's also the concept of the greatest lower bound. GLB. It also has a name. So if you give me a set and I take its greatest lower bound, we give that a name. If it exists, we use the term infimum instead of supremum. Okay. And we write inf, INF, instead of sup. Okay, inf A. So greatest lower bound of a set A you'll write the imp of A. Okay. Now, on your homework, you'll show some properties about this. So, for instance, on your homework, you'll show, in fact, that the infimum of a set, if it exists, is minus the supremum of the set where you negate everything. Okay, so this will be in your homework. This symbol will be defined as take the negative of everything that's in A. Okay. The infimum may not exist, but it will exist, of course, if the set is bounded below. Okay. If a set is bounded below. So now this is not true in Q, but it's true in R. So it's basically the corresponding property. Instead of the least upper bound property, R also satisfies the greatest lower bound property for the same reason. And you can guess what the greatest lower bound property is. It just says if it's set's bounded below, it has a greatest lower bound. Okay. Yes.
When we're putting things like the infimum is the opposite of the supremum,
Mm-hmm.
will we be thinking of R as the cuts, or can we think of it as R?
From now on, you can think of the real numbers as R, as the real numbers you're used to thinking of. Okay. Unless, of course, it says to think about this in terms of cuts. Like one of your homework assignments asked you to think about cuts. Okay. I mean, this particular definition of real numbers as cuts, I mean, it's just one possible way to construct the real numbers. Later on, we'll see there's another way to construct the real numbers in terms of Cauchy sequences, but we haven't talked about what a sequence is yet. Okay. Okay, excellent. So I hope at least you've begun to see that this concept of supremum, the least upper bound, it's a hugely important concept. It's what makes the real numbers different from just the rationals. It allows, as you'll see to come, the idea of a limit, okay, which is fundamental to calculus. Okay? And so this property plays a huge role, and so I do want to talk about properties of supremum. But we're going to do that after a couple of minute break. Okay, so let's take a couple minute break and we'll resume. We're ready to resume. So we have established the least upper bound property for the real numbers as a very important property, and I want to talk about some consequences of the least upper bound property, and then I want to talk about some properties of the least upper bound, since we're going to be using them quite a bit. Okay, so that's the plan for the second half of this lecture. So let's discuss some consequences of the least upper bound property. So one of the consequences is something that's maybe self-evident, but it's important to see how it follows from this least upper bound property. And that is something we'll call the Archimedean property. Archimedean. It's hard to spell, and probably that vowel there is the most troublesome. Archimedean property of the real numbers. And what it says is the following. If you give me two numbers that are real, and let's demand that one of them, x, be bigger than 0, then I claim the following is true, that there is a positive integer, little n, such that you can multiply n times x, and eventually one of those multiples will be bigger than y. Okay? That seemed pretty self-evident. Katie, question? Question? Yes, yeah, oh, yeah, if y is negative and n equals 1 will suffice. Okay? Okay, so this seems like a very innocent property, but it's a consequence of the least upper bound property. So let's prove this property. Actually, maybe I might even just point out some other things before I prove this property. So it's equivalent to thinking about the following statement. I claim, if you like, if I just let y be 1, then really what this is saying is if x is bigger than 0, then there exists a natural number such that 1 over n is less than x. Okay, so some reciprocal of a positive number is going to be eventually smaller than x. Yes, Emil? Do the rationals have the Archimedean property? Let's see. So it's, yeah, so let's see. So let's just check. If you have two rationals, one of them is bigger than 0, then there's a positive integer that makes, whose multiple is eventually bigger than that other positive integer. Yeah, it does have the Archimedean property. Now it's, yeah, okay. So let me come back to this, okay? Because yeah. So there are some distinctions to be made, but let me come back once we have the argument. So how would I prove a statement like this? So if I want to think about this, one way to think about it is the following. Let's suppose I have a number line here. So here's the proof. Let's look at the collection of all multiples of x, okay, for n in the natural numbers. Claim is that this is eventually bigger than y. Now, if it's not true, we'll hope to get a contradiction. That's the claim. So this is a proof by contradiction. Let's consider, so I'll make this a statement by saying consider A. So if A is bounded, if A were bounded by y, that's what it would mean for the statement to not be true, is that y is bigger than everything. So in other words, nx is less than y for all n. That's the contradiction we're beginning with. Then what would that mean? Well, then y is an upper bound for A. But A is a collection of numbers, right? So, and it's bounded above. Therefore, it has a what? A least upper bound. So A has a least upper bound by the least upper bound property. Let's call it alpha. So the picture that I'm going to have here is I have a bunch of multiples of x, okay? And if for some reason these never, ever exceed some number y, then this collection of dots has a least upper bound, which I will call alpha. Let's say alpha is right here. Okay. All right. Good. So how is this going to help us get a contradiction? Well, if this is a least upper bound, what has to be true about the least upper bound? What has to be true about anything smaller than alpha? Not an upper bound. Good. So then alpha minus, let's subtract something convenient. How about subtracting x? Since x is positive, this is smaller. Alpha minus x is not an upper bound for A. Okay. But if it's not an upper bound, that means what? Hence, alpha minus x is less than some multiple. Let's give that multiple a name. What would you like to call it? How about something specific? Instead of little n, how about little mx? And we'll tell the reader for some m in the natural numbers. Okay? So now I've just subtracted alpha minus x, and I get a position over here, perhaps. Let me use a different color. Maybe this is alpha minus x. Okay. Help. Oh. Okay, then what? So alpha is less than mx plus x, otherwise known as m plus 1 times x. Okay, good. So there's all of you are trying to get to a contradiction. What is a contradiction? If alpha is less than m plus 1 times x? Good. Then alpha isn't an upper bound for A as we suggested. Alpha is not an upper bound for A. A contradiction. Okay. So we've achieved a contradiction. Therefore, nx eventually has to be bigger than y. Okay. So yeah, so I guess Emil had a question earlier, which was, gee, well, doesn't the rational numbers have this property as well? And the answer is yes. So let's see, could you use the same proof? No, why not? There's no requirement for a least upper bound. That's correct. For the set A. So if you were to show this property, you'd have to show it a different way. Yeah, and so if you think about this just a little bit, what did we use this property? We used it in order to show that alpha minus x is not an upper bound, and in this case, whatever x is, you'd have to make this jump a different way. Okay, excellent question. Okay, so this is an innocuous statement, but it actually has another consequence which is worth pointing out and maybe a surprise to some of you. And that's the following theorem. If you give me any two real numbers between any x and y in R, let's say x, you might as well assume, is less than y, I claim there is a rational in between them. There is a q in q such that x is less than q is less than y. Another way we say this is we say q is dense in R. What does that mean? It means formally, it means that if you take any interval, you can always find a rational in that interval. So here, x, if you give me two endpoints, I can always find a rational that's in between any two real numbers. Okay? Really? Okay, now why is that? Well, let's prove it. It's actually not too hard to show once we've established the Archimedean property. So let's use this fact. So I'm going to think about the Archimedean property in its equivalent form. You give me a number, there is a reciprocal that's smaller than that number, that positive number. So let's choose n such that 1 over n is less than the distance between y and x. Okay? You can't stop me from doing that, and this is the Archimedean property. Okay, that's where at least one place we've used it. Okay, so let me draw a picture because this may help. Here's y, here's x. Look at their difference. Find a reciprocal who's smaller than that difference. And if you imagine these numbers being really, 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 really close together, this number n might be really, really, really large. Okay? Okay. Now, consider multiples of 1 over n. So start multiplying 1 over n. 1 over n, 2 over n, 3 over n, 4 over n, 5 over n, etc. What do you know about the multiples of 1 over n, also by the Archimedean property? Multiples of anything. They're unbounded. Okay? They'll get as large as you like. So these are unbounded by the Archimedean property also. I'm doing this argument slightly different than the book, but I think this is probably an easier argument to see. So these are unbounded. Well, what does that mean? Well, if it's unbounded, eventually they're bigger than the number x. Okay. So I'm going to choose the first one, the first multiple, such that m over n is bigger than x. Okay. So I picked the first one that just got beyond x. So here you have a bunch of multiples. And there's a first one that, so this is 1 over n, 2 over n, etc. Eventually, the first one that just crosses x. And so now I claim m over n is in fact also smaller than y. That is, that first red point actually has got to live between x and y. It won't also be beyond y. Why is that? If not, then what would we have? We would have the following inequalities. We'd have m minus 1 over n is less than x, agreed, because m over n is bigger than x, and it was the first one to do that. And you'd have m over n bigger than y, excuse me. But together, these statements would say that 1 over n, but these two statements imply that 1 over n is in fact bigger than b over a contradiction. Why is that? Multiply both sides by, sorry, not by b minus a, y minus x. Sorry, excuse me. I'm just thinking in terms of a's and b's. Multiply this by minus to switch the inequality and add the two inequalities. and you get 1 over n as the difference on one side, and y minus x is the difference on the other. Okay. So between any two rational, real numbers, there is a rational number. They're dense in the reals. They're everywhere. Okay. You can find them in any small interval, as small as you like. Okay, very good. Let's conclude by listing some properties of suprema, which will be very useful to you as you work with them. And they're all rather self-evident. Of the suprema, this least upper bound idea. So the first property, which you might want to familiarize yourself with, is if you have an upper bound, I'm going to abbreviate upper bound by UB, for some set A, that this is true if and only if what's true about the supremum of A. Good. The supremum is less than or equal to gamma if and only if gamma is an upper bound. That should be evident from the definition. Okay, this is the least upper bound of the set A. This is some upper bound. Okay. Well, what about the following? If suppose you know that gamma, that for all little a in big A, little a is less than or equal to gamma. What does this imply? If you know that for everything in a set, gamma bounds that thing, then what? Then gamma is an upper bound, or another way of saying it is the supremum is what? Less than or equal to gamma. With me? Okay, again, self-evident, but a worthwhile property to record. What does this mean? This means, in effect, what this means is if you have an equation that says, an inequality that says alpha is always bounded by some gamma for all alpha, then you can put sup without changing the inequality. Okay? Yes, Jenny? It does. Well, let me be very careful about this. Okay, no. Okay. Let me write down the second thing. And let me address your question here. So suppose you have the same statement for all alpha a and big A. A is just less than gamma. What can I conclude about the supremum? Here's one case where you might be a little careful. What can I conclude about the supremum? Okay, yeah, so you might be tempted because of the strict less than here to think that this is just a strict less than, but it's not. There is an equals here, less than or equal to. The most you could conclude is that the supremum is less than or equal to gamma. And the reason is, you could just think about this, is when you take the supremum, remember, it actually could achieve the bound even if everything's less than gamma, right? So, for instance, look at all the numbers all the negative numbers. Certainly, all the negative numbers are strictly less than 0, but the supremum of the negative numbers is 0. Okay. Okay. So Jenny's question was, can you make one of these? Can you make this an if and only if? So if the supremum is less than or equal to gamma, is it true that in fact everything is less than or equal to gamma? Yes, that's just by definition. This is the least upper bound. This is some other upper bound, so this is going to be an upper bound. But that's follows from the definition, if you like. Okay. Okay, good. Let's write down another property here. What if you know the following? If gamma is less than the supremum of A, well, here's another thing we've implicitly used already, but worth noting. If you have a number that's strictly smaller than the supremum, then what does this imply? There exists a little a in big A such that what's true? Little a is bigger than gamma and what? Less than or equal to the supremum of A. So if there's a number smaller than gamma, than the supremum of A, there must be something in the set that's strictly bigger than gamma. It might be equal to the supremum. So that's why I'm going to put that picture there. Okay. Again, a useful property. So, if I wanted to summarize how you might show that something is a supremum, if you might show an upper bound is the least upper bound, there are two strategies, right? First, you show it's an upper bound, and then you either show that anything that is smaller isn't an upper bound, or you show that if something is an upper bound, all the other upper bounds are bigger than it, right? There are two ways of showing that something's a supremum. Let me give another property here. What if A is a subset of B? What can I say about the supremum of A and the supremum of B? Okay, good. The supremum of A is less than or equal to the supremum of B. Really? Why? Feels right, but how would I show it carefully? So this one might require a little more justification. Well, if A is a subset of B, then everything, so how am I going to show the supremum is less than blah? How am I going to show the supremum is less than blah? I'll show that blah is an upper bound for A. Okay, or if I like, I'll show that blah is bigger than everything in A. Is blah, which is sup B here, is sup B bigger than everything in A? Yes, because everything in A is in B, and then therefore less than sup B. So why? For all A in little a, A is in B, so A is less than or equal to sup B. And then by property, I don't know, which one is it, B? Sup A is less than or equal to sup B. Okay? So maybe you get a sense of how you're sort of implicitly using these properties here. Okay. And I'm going to finish with a property that might be helpful for one of the homework problems. I think it's the next homework, maybe not this one, but property F. What if you want to show sup A equals sup B? The supremum of two sets are exactly the same. How would you do that? What would be a strategy? Yes?
You could show one's less than or equal to the other, and the other is also less than or equal to it.
Okay, you could show that the sup of A is less than or equal to sup B, and sup B is less than or equal to sup A. What would that involve? Okay, using some of these properties, yes, very true. Let me suggest the following. Here's one way to think about it. Now, see, if you're lucky, the two sets might be the same, right? Then it's easy to see why this is true, to prove what you just said, right? But that's not necessarily going to be the case. So here's one strategy. Let's show that for every little a in big A, there exists a little b in big B such that little a is less than or equal to little b. Would you agree that this would be enough to show that sup A is less than sup B? Why? Well, it's kind of like this argument, except you don't have the fact that little a is in B. But if you can show little a is less than little b, then little b is less than sup b. And therefore, sup b is a bound for all things in A because there's an element for each of them that works, and therefore bigger than sup A. And then similarly use a similar method for greater than or equal to. Okay? This might be helpful to you in solving one of the homework problems. Okay, excellent. So we've talked about the least upper bound property, and it's something that distinguishes the reals. Next time, we're going to start talking about the complex number field. Okay, that's the plan. See you next time.
I was wondering if we can